Hello and welcome. My name is Hamed Rastgoo and I'll be representing University Push Malaysia for the Material Lecture Competition 2021. My topic is actually going to be about laser joining of dissimilar materials. And my presentation is actually going to illustrate and explain three key words from the title itself: laser, joining, and dissimilar materials. So to start off, we're going to talk about dissimilar materials, what they are and how to identify them. Then we're going to talk about the different joining methods that have been established through time and what are some of the more relevant ones used today. And last but not least, we're going to talk about lasers and their role in the grand scheme of things. So without further ado, let's begin. So first we'll talk about dissimilar materials. Now, in order to understand them better, we're going to answer two main questions. One, what are dissimilar materials? And two, what is the purpose of joining them? Because as we're going to understand, it's very difficult to join dissimilar materials due to their characteristics. And we're going to talk about these questions in detail. So first off, what are dissimilar materials? So in general, materials with different core properties are often classified as dissimilar materials. Sometimes they're called monolithic materials or individual materials as well. These comprise of such as metals, polymers, and ceramics. Now, on a side note, I would like to add, it is common and very much possible for two or more materials within the same group to identify as materials, dissimilar materials as well. For instance, we have carbon steel and aluminum. Obviously, they're both metal. However, due to the differences in composition, joining them is actually very difficult at times. That's why they're often known as dissimilar materials as well. Just a little bit of a side note as we go along. So now we're going to talk about what is the purpose of bonding dissimilar materials overall. Because of their different characteristics, since these are different materials from a core perspective, it's actually very difficult to join them. So let's see, why should we go through all of this process and through this very tedious process in order to join them? So the main goal here is to obtain a more desirable combination of properties. Basically, trends such as lightweighting, increased performance, and functionality have definitely increased the use of multi-material hybrid structures nowadays. One example that we can see here is whenever we want to join metals and plastics. So when we talk about plastics, one of the characteristics are that plastics are very light in terms of weight, but at the same time, they don't have a really strong weight to body ratio. And on the other hand, metals are very strong. They have a great tensile strength, but they're actually quite heavy. So what dissimilar materials actually does is that we now ponder the question, can we take the lightness of plastic and also at the same time take the strength of metals and combine these two great advantages, two great characteristics and properties, and combine them into one single entity? That is the main question here. And to answer it, yes, we can, but it's a little bit more difficult than that. And that's why we transpose into joining of the similar materials. Now, in order to understand this better, we're going to show a hierarchy. So from this, we can actually see that this is actually not a very new topic. This has definitely been discussed in the past before. In fact, this is so old that we can see conventional methods and modern methods as well. So these traditional methods, they're actually not quite insignificant. They're used to this date, and the only main difference between them, conventional methods and modern methods, is that traditional methods are not usually used for long-term solutions or long-term joints. After some time, they might need a little bit of maintenance, or the joint will just be weak for them to hold on anymore. That's why these are known as traditional methods. Modern methods such as thermal fusion joining and hybrid joining actually fix this issue by making it quite inseparable, and that bond is quite difficult to break. But nevertheless, we're going to talk about thermal fusion joining here, and we can see there's a lot of different types. We have friction welding, brazing, electric arc welding, all the way up to the more recent one, such as high energy beam welding. And underneath that, we see laser joining. So from this graph, we can see that laser joining is one of the more modern and one of the more recent methods, and it actually holds a lot of weight on its shoulders. It's taking a lot of prestige among all these different components, and we're going to talk about why this method is not only useful, but it's actually better in comparison between these other different these other methods. So, with that said, we can finally jump into laser joining of dissimilar materials, the very topic that we started this presentation on. So this section is going to be completely dedicated to understanding a brief history of lasers, the fundamentals of lasers, and naturally we're going to talk a little bit depth of the joining process itself. So to start off, let's look at the brief history of lasers. And now I cannot stress this enough. Way back in 1916, the man himself, Albert Einstein, suggested the fundamentals of lasers himself. However, as he was ahead of his time, it took almost 40 years until the first laser machine was built by none other than Theodore H. Maiman himself. So even though this idea was composed way back in the earliest of the 20th century, it was only half a century later that the first prototype was built. But nevertheless, we got it. And now we move on to the third industrial revolution, where mass production was key for many industries. So it doesn't come by surprise that only 10 years after the first prototype was built in 1970, people began to use lasers to weld materials together. However, at the time, they only used similar materials such as metal to metal or plastic to plastic. But that changed by 1995, which is at the end of the 20th century, where we saw people testing this on dissimilar materials as well. This was when a lot of industries saw the potential of laser welding dissimilar materials and decided to fund a lot of money into researching them as well, which is why when we come to the beginning of the 21st century in 2005, a lot of these industries, high industries such as aerospace and mechanical engineering industries, funded these research facilities to get a more better understanding of laser welding. And it comes to no surprise that only 10 years after the start of the 21st century, there was a breakthrough in investigating laser welding on an atomic and molecular level. So at this point, we can see that laser welding definitely served its purpose of achieving industrial solutions. However, at this point forward, it was much more than just achieving industrial attributes. At this point, people were researching it to understand what actually happens when we fuse or bond two materials using lasers. And it took no surprise that in 2014, we actually got an identification for the main parameters in laser welding. This is actually a breakthrough in its own right as well, because it solidified laser welding into that nowadays anyone who wants to perform any type of laser welding, they can just easily play with these parameters and make the outcome much more simpler and more precise. With that said, we do enter the fourth industrial revolution and the present day. Nowadays, with automation and a lot of software coming into play, nowadays people are analyzing laser welding using finite element method, such as simulations and so on. Because laser welding takes a lot of specimens and it goes through a lot of trial and error, people have found a good way to use simulation to their advantage to save cost and of course, ultimately time. Just running through these various applications through software, we can get much more faster results. However, it's still fairly new, but it definitely has a lot of potential, and we might actually see this coming up in the next decade or so. But with that said, we now get to the fundamentals of laser joining. So what are lasers actually? So laser, ironically enough, is actually an acronym for light amplification by stimulated emission of radiation. This is a little bit difficult to understand, but to put it simply, a laser is a device that converts light into a focused high energy beam. So the whole purpose of laser is that we have a source with a lot of energy, and what lasers do is that we try to focus that high amount of energy into one specific location, or as we call it, one specific spot size, which is tremendous. having that much energy and focusing it into only one heat affected zone. That is the idea behind it. However, going forward, we can actually identify the characteristics of laser joining. This is why this topic is so appealing to many of these industries, is because that laser joining is used for high precision manufacturing, joining of complex shapes and microparts, and this is a non-contact process. So it makes the entire experimental procedure so easy because of the fact that it doesn't have any kind of contact with the material. The device is actually within distance. So these are just the basic fundamentals of laser joining. Now we want to talk about the process itself. This is where we get a little bit deep. Now, to understand this, we're going to pick only one particular example, and that is metal and polymer. Naturally, if you want to pick metal, ceramic, or polymer and ceramic, we will get different types of outcomes. So in here, we're only talk about one of these things. And this is how the process begins. So in the first phase, laser beam passes through the polymer and irritates the metal surface. As we can see from the picture, the laser has passed through the polymer and has made contact with the metal surface. So what happens next? The polymer is heated up and bubbles are formed. Now this happens, and we understand this because we know the characteristics of these two materials. Obviously, the melting temperature of polymer is much less than metal. And at the same time, the boiling point of polymer is also less than metal as well. So while that laser is heating that polymer, it is surpassing its boiling point while not even reaching the melting point of the metal itself. Of course, in some cases, depending on the metal, we might see that solid turn into a little bit of liquid as the metal also melts, but it's only on a surface level. Nevertheless, that polymer reaches its boiling point and starts to bubble up. So what do these bubbles actually do? So after these bubbles are formed, we no longer need the laser. The laser device actually shuts down and the environment surrounding these two components starts to cool down. So these bubbles push the molten polymer to stick onto the surface on the metal surface, which is amazing. Now that bubble no longer has anything to heat it up. So the bubble starts to go away, and while it does that, it solidifies that polymer to the metal surface. And in the fourth and final stage, the molten polymer solidifies and the bubbles remain on the upper side. And in theory, those number of bubbles actually identify how strong the joint between the polymer and metal can be. And so this was a very in-depth look at what happens when we laser two materials together. With that said, we're just going to have a quick recap of what just happened. So first we talked about what are dissimilar materials and how we can identify them. Then we went to a question of why should we actually combine these different materials, since they're actually quite difficult to join, but we found a really great purpose for them, not only on an industrial level, but on a scientific and research level as well. They pose a lot of advantages for us. And then finally, we talked about how to join dissimilar materials, which was by practicing both conventional and modern methods so that we can understand the relationship between these two materials as well, and to understand what happens when we use laser joining. All of this leading up to the laser joining of dissimilar materials. And yes, on the surface, we do talk about joining two very different materials using a high energy beam, but on a much more deeper and intellectual level, we are actually discussing the relationship between two different materials and how we can use their criteria and use their characteristics to our advantage. So, using laser joining, we were able to unravel some of the hidden secrets of materials as well. Because once we heat up the polymer, or once we heat up a material, we start seeing its physical and chemical properties change. And understanding what happens could lead to a whole new gateway of researchers and so many different questions about materials as well. And with that, we can actually increase our grand knowledge of materials. So on a surface level, it is about joining two different materials, but on a much more deeper level, it is about finding what actually happens and how can we actually increase our knowledge of Materials Science. And with that said, I would like to end my presentation here. Thank you very much for listening. That is all from me. Thank you.